Hello again. In this video, we're going to discuss the very important concept called the derivative. Let's get started. Follow my cursor as I go. So we're going to define the derivative. Let a be less than b, and let c be an element in this open interval, ab. Let the open interval be a subset of d, which is a subset of the reals, and let f be a function from d to r. If the limit x goes to c of f of x minus f of c over x minus c exists and is finite, we don't want it to equal any type of infinity, then f is said to be differentiable at x equals c. And let d prime be a subset of d, let d prime, which is a subset of d, be the set of points at which f is differentiable. So, in other words, where this limit exists. D prime is a subset. D prime could equal d itself, but it doesn't have to. Now, in the examples I'm going to pick on, I don't want to get into analysis. D prime will usually equal d. If not always, almost always. But anyway, then we can define the function f prime, mind you, from d prime to r, such that f prime of c equals this. Sure, d prime, after all, is where this limit exists and is finite for all c in d prime. F prime is called the derivative of f on d prime. Technically, it's hollow if I don't say on d prime, because I need to specify the domain at which we're on. But a lot of times I'm going to be a little hollow and lazy. And when d prime equals d, and because most of the time I'm going to let d prime equal d, and it's going to be either given or obvious what the domain d is, I'm going to be lazy and just call f prime the derivative of f, even though that's technically been a little bit hollow and sloppy. If y is used in place of f of x, I will refer to the derivative as y prime or dy by dx. And really, I should say, if I was to be totally correct, it would be the derivative. It would be the derivative on d prime. But I'm usually sloppy and I don't bother putting on d prime. But I'll put it there if you want to have, perfection or whatever. Now, there's a word of warning a little bit. Dy by dx here, that's not exactly a fraction. There's a limit involved, okay? It acts like a fraction in a lot of ways, but at the end of the day, there's more to it than just a fraction. It's a limit of a fraction. It's the limit as x goes to c of f of f of x minus, or y of x minus y of c over x minus c. Instead of f of x, we say y of x here. So that's what I mean by that. We're just using y of x instead of f of x. But anyway, there's that. And there's one thing I should note. Sometimes we denote the derivative as, like the derivative at c, and I'll type this as I'm writing. The derivative of f is also denoted as, or the general derivative is d by dx of f of x. So sorry for the pause there. I'm just typing this stuff out. D by dx of f of x, or df by dx. You need to get used to all of this. But now you're like, well, Jason, what about at a specific point c? The derivative of course, f prime of c, we already know that. The derivative of f at x equals c is denoted, well, let me insert this stuff. Sorry for the pauses, but let me go ahead and get this. I want to get this done. df by dx, and then at x equals c. So what we want to do is draw a vertical slash, and I'll need subscript. So vertical slash here, and then x equals c here. So this means the derivative of f and you do the derivative first, and then after you do the derivative, you take this, really you're just taking this limit here. But later on, when we get to the shortcuts, like you can do df by dx that'll work for any x, and then you can throw in x equals c after you do the derivative. But I've not shown you those shortcuts yet. Or, and then this shouldn't surprise you too much, I forgot to do the other one. So d by dx of f of x, and this is more honest because there's more going on. This makes it look too much like a fraction, and so does this. Again, for the same reasons as dy by dx. This is more than just a fraction, it's a limit of fractions, but it will act like a fraction in a lot of ways, as we'll see as time goes on. But in truthful honesty, there's a little more to it than just a fraction. But anyway, and since this is at a specific point, I need to put the same vertical slash and the same x equals c down underneath that slash. So there's that. That's this is at a specific point. This is just the general rule at any point. So what you can do, if you'd rather, you can just go ahead and just do this. And let's say you decide that you want to pick on a point like x equals 5. You could throw 5 in. After you do this, you could throw in 5 or whatever. Now, to do this just bold-faced without a limit, you're going to need a shortcut formula, and that shortcut will give you d by dx of f of x for any x. It will be broad. But then you can, after you do that, after you use that formula, then after the fact, you can throw in c, like if c equals 5 or whatever. It could be a bunch of things. But anyway, in general, it can be a bunch of things. But anyway, I'll talk more on that as time goes on. But I know this is hazy. I know right now you're probably feeling a little bit intimidated, and it's only natural. It's just the material. But let's do some examples, and this should fall into place. So don't give up on me. I know this is a little bit more intimidating than the stuff we've been going over. Let me give you an alternative definition, and all I'm going to do in this alternative definition is just, there's another way I can write this limit right here where my cursor is. I can write it, the limit is h goes to 0 of, I can replace x with c plus h, and I can replace x minus c with h. Like if x is c plus h, x minus c is going to be h. So if I can take the limit as h goes to 0 of f of c plus h minus f of c over h. And in this alternative definition, that's all I'm going to do, literally. I'm just going to show it off that I can do it. I'll probably use the main definition more, but you can use either one. They're both just as, one is just as valid as the other. So again, I have the same old stuff, and I just replace the one limit with the other. That's all. I won't bother reading all this again. And I forgot to put in, now the same goes for my notations. I kind of forgot to, I need to copy and paste this just so you'll have it. It's just as good for alternative definition as it is for this one. They're the same thing, really. No joke. They're pretty much the same thing. And, well, okay. So there's all that. So this is just the alternative definition. Now, I know you're probably feeling a little intimidated, and I understand, but the example should open things up. Now, at first, I'm going to push limits. Now, later on, I'm going to give you the shortcut formulas, and we don't have to push these painful limits every time, but we need to push the limits so I can show you what things are all about and what the derivative, you can get an idea what the derivative is. The derivative at a point C is just this, the derivative of f at a point C is just this limit, okay? Now, I need to give you a concrete C like 5 or -2 or something, and I need to give you a concrete f like f of x equals x squared or whatever. We could have a whole bunch of functions and a whole bunch of numbers at which that function is differentiable, aka when it's differentiable at a point, this limit exists at that point, okay? So, well, let's see. And actually, you know what? If it's differentiable at a point, then at an interior point, and you know what, guys? There's something I need to point out here. Differentiability happens at an interior point. What I mean by that is, you remember from the very beginning, C is in this open interval AB. Here a little later, I'll show you, we can sort of do we can do a one-sided differentiability, sort of like we did continuity, but a little bit is lost. We like to do I don't like it as well. We like to have C as an interior point. To be truly differentiable, you need to have an interior point to be differentiable at that point. Now, if you're an endpoint, well, it's a gray area. You're differentiable from one side, but from the other side, well, you might could argue, but we really, with differentiability, we want to focus on interior points because that's where the good stuff is. You could say that at the left endpoint, later on, I could do a closed interval AB and say we're differentiable from the right at A and from the left at B. But, and that will come in handy in some advanced math classes from time to time, but it's not as important as differentiability at the interior point. So let's just stay interior for now. So when I say from now on in this class, when I say differentiable, I mean at an interior point. So if I'm differentiable, I should have been careful a minute ago. Yes, this limit exists, but also that, I needed to specify that from the first place that this C is an interior point at which F is defined. So F will be defined there. As it turns out, if we're differentiable at C, we're going to be continuous at C. Now the converse is not necessarily true, as we'll see later. You could be continuous and not differentiable, but if you're differentiable at C, i.e. if this right here is true, then the ordinary function F, when I say continuous, I mean the ordinary function F will be continuous at C. I don't necessarily mean F prime, I just mean F is continuous at C. If F prime exists at C, then F will be continuous at C. But that can actually be proven without a lot of heartache at all. But in this class, we'll take it for granted. It follows from the limit laws and all that, but anyway, so if C is an interior point at which F is defined, and if F prime of C exists, aka if this limit exists, then F by definition is said to be differentiable at x equals C. Or you could say F has a derivative at x equals C, but that feels a little sloppy. It's nicer to say F is differentiable at x equals C, okay? So there's that. And again, this alternative definition, all I did was just use this limit instead. That's the only thing different, okay? They're the same limit, by the way. They mean the same thing. And we can prove that too, but by the way, I'm taking that for granted as well. You're like, well, Jason, can you prove that? You can, but please let me take it for granted. Take it for granted that this limit right here is the same thing as the limit x goes to C of fx minus fc over x minus c. So that we had from a few minutes ago. So just take my word for it without proof that they are the same limit. They'll give you the same number. A number that we call f prime of C, okay? So C is an interior point at which we're defined. We assume that's true from the get-go. And if it's also true that this limit exists, then we're differentiable at C. So C is an interior point at which is in the domain of D. It's an interior point of that domain D, which is the domain of the function f. When I say domain D, I mean of the domain of the function f, to not be hollow. Okay, and again, to get from the top to the second definition, you replace x with c plus h, and that's all you do. And as x goes to c, h is going to go to 0. It would have to, and that's sort of how the proof goes. That's just an informal idea of how the proof goes. That's not proof, but that I'm not going to do the proof anyway. So let me do an example real quick. I've spent a lot of time, going through the definition. Let f of x just equal a constant, like 7. You could say f of x equals radical 7 or something crazy, just so it's a constant. For all real x, then we get, for any real c, the limit x goes to c of f of x minus f of c over x minus c. Well, f of x and f of c both equal 7. So it's 7 minus 7 over x minus c. But hey, that limit is just 0, because as x gets arbitrarily close to c without touching c, this is 0 all the way. So the limit is 0. And guys, by the way, the domain D of f and the domain D prime of f prime, they're the same. They're all real numbers. So we're assuming, and this is D is all, this is a function from the reals to the reals such that f of x equals 7. But I just wanted to point that out. And of course, it's neither injective nor is it surjective, not even close. But we don't, in general, I'm never assuming bijectivity unless I come out and say it, by the way, okay? So anyway, here's that. So the f, you could say let f be a function from R to R such that f of x equals 7, but I was just lazy and took the domain D for granted, and D prime will equal D here. So there's that. And for any point C, you could let C be 20. So if you replace C with 20, you know, you'd have f of 20 here and 20 here, but you'd still get 7 minus 7 over x minus 20. You'd still get 0. You could let C be whatever. C can be any real number under the sun. So there's that. Now, a little less trivially, let's say f of x equals 7x for all real x. Again, my domain D and my D prime are going to be all reals, so f is a function from reals to reals. Then we get, for any real C, this limit right here, f of x is 7x, f of c is 7c over x minus c. But hey, wait a minute, we can, by algebra, on the numerator, we can factor out a 7 and put parentheses x minus c over x minus c. But lo and behold, these x minus c's will cancel, and I get limit x goes to c of the number 7, but remember, that's just 7. So my derivative at any point is just 7. And then if I go back, and here, guys, this is not exciting. This is what I talked about a minute ago. I used 20 instead of 10, but if c was 10, you'd replace the c's with 10s, and you'd still get 0. And if for f of x equals 7x, I'd replace the c with 10, and I'd still get 7. Okay, so there's that. And here's that. And you can filter out that 7, by the way, and these will cancel, and there you go. Now, again, if f of x, what if I spice it up a little bit, and instead of just 7x, now let's consider f of x equals 7x minus 5. And again, from reals to reals. And then, and if I let c equal 10, or if I just want to stay with the generic letter c, doesn't matter, f prime of x equals the limit x goes to 10 of this definition. Now, but f of x is 7x minus 5. Now, be careful. You're minusing f of 10. So you got to put brackets or parentheses, just whichever, around this term here. You're minusing all of this stuff inside the brackets over x minus 10. But you distribute that minus sign, you get minus 70, but be really careful. You're minusing an already negative 5, you get plus 5. All over x minus 10. Lo and behold, this negative 5 and plus 5 will self-destruct. They'll cancel. And you just get 7x minus 70 over x minus 10. And you can filter out that 7 like that and cancel the x minus 10s. And you just get 7. You know what? The derivative is acting an awful lot like slope, particularly the slope of a line. You remember y equals 7x minus 5? The slope is 7. And that's what we got for the derivative. And if y equals 7x, the derivative is 7. Let me space there. So the derivative is 7. That's the slope of this guy, y equals 7x. Now, if y equals just 7, not 7x, mind you, if y just equals 7, the slope is 0. Remember, that's the horizontal line, y equals 7, at a constant altitude of 7, so to speak. The slope of a flat line is 0. That was our derivative. That's no coincidence. Derivative is slope, you know, visually speaking. The derivative is a slope. Now, the derivative visually is the slope of a graph at that point. For a line, the derivative is the slope of that line, period. Now for a curve, the derivative is the slope that you would, of the tangent line you would get if you broke off of that curve. But I need to go over tangent line. But if you broke off of that curve and went flying off on a quote-unquote tangent, the slope of that tangent would be the derivative, but I need to say more about that. Let's stop this video. Thank you. See you on the next video.